Hi everybody, my name is Miguel Jimenez and I'll be leading the tutorial demonstration of OceanSpy on SciServer using analyzing data output from the LLC4320. All right, so the first thing I'm going to do, I'm going to share my screen. Let's see over here. You should be seeing my screen, I hope. And right now we're seeing the login for SciServer, first steps of the log SciServer. And you should already at this point have an account. If you don't, I suggest you look at the tutorial video of how to opening an account. It's free. And the only things that you need to have a university affiliated email. Other than that, it's pretty straightforward how to open one. Okay, so we're here. I'm going to close this guys over here now. So we're looking at my different containers. I'm going to pick this one, which I know it actually has the right tools to run this notebook. At the same time, I'm going to be opening. Sorry about that. Hain groups container. All right. So with that, I'm going to switch to Jupyter Lab. And what I want to do, the first step to here is get the notebook from GitHub that we want to run today. So I'm going to clone it into my Scratch directory folder. Let's see. Here it is. Okay, great. And what we want, this is a repository for Thomas Hain, the research group that I'm a part of. So I'm going to look at this repository. So this repository contains 2 tutorial notebooks. The video that I'm recording right now actually details how to run this tutorial notebook right here, LLC4320. Alice Dickey actually has another video for how to run LLC90 on SciServer, which is the echo data set. We're just gonna go ahead and clone everything here into local directory. It should take about a minute. Other than that, after that, it will be straight to go. So now I've done everything essentially in the terminal. Now we can actually navigate it to that on this left tab. So temporary, my account, and here it is. So here are the notebooks. And let's go ahead and open this guy right here. Perfect. So this is a notebook that we'll be running today. It's actually quite slower than the notebook that Ali runs, mostly because it's just bigger data set. So what we're gonna do here to try to keep this more interactive, this video more interactive and easier to talk through is that I'm just gonna go ahead and run all of the cells right at the beginning. And I'm just going to go essentially describe the cells each by if they need to be described. But essentially, yeah, so this is it. So we have the notebook. This is a little bit of demonstration of what OceanSpy does. Anybody who's familiar with the LLC type of grid is that they have a complex topology in which you divide the domain into different phases. Each of them have not each of them, but some of them have similar orientation, but that sometimes they're not exactly the geographical orientation. So you need to have to figure out how to do, especially if you're interested in subdomains that are contained within an interface between 2 different phases that have different topology. You need to figure out manually how to make sure that the physical quantities actually make sense. For example, transport across one phase to the other one, that's actually the relevant transport. In this case, OceanSpy does it for you. And this is a really clever way because it uses a lot of the Pangeo environment, which essentially is built upon using X-arrays. Anybody who's familiar with X-arrays knows that these are similar to Dask or NumPy arrays, but the advantage is that they're lazily evaluated. And they can actually be scaled up, which is very useful for us, especially when scaling up memory or data, which is the case that we're actually talking about here. So this is one of the essentially the main point about the scalability of the software package OceanSpy. And what it does is that it rearranges the domain lazily in a way so that whenever you're looking at a subdomain, say, for example, in this case, we're interested in North Atlantic or subpolar North Atlantic and a research group, then you can actually just extract data from it lazily into a separate kind of object. And that cutout, which will have look a little weird, will have the right orientation, the right topology, and you don't have to worry about the complex topology and have to figure out the right exchanges between different faces. This is, I have to say, this is also a collaboration, a big project. The Poseidon project is a collaboration between Johns Hopkins, MIT, and Columbia. It's a really, really interesting group. And right here, just before I move forward to the notebook, I just want to say, essentially what we're doing here is running code within SciServer, which is very useful because one of the biggest issues and challenges of doing analyzing model output, especially at this size of model output, which you'll see is about 80 terabytes or something, is how to get the data, how to transfer the data into your local computer or some like a cluster within your university, your institution. And usually these data is kind of stored somewhere in a supercomputer. So getting the data just to do a plot, it can be very, very difficult and challenging. In this case, what SciServer does is actually brings the data into your local environment. So we are able to run a notebook. We have the right environment. We don't need to worry about defining the right environment, already has the right environment. And you're able to run code as if the data was local to the code, which is incredibly useful for accelerating science in general. So this is what you're doing. Again, like I said, you don't have to worry about where the data, defining the data, the location of the data, how to transfer, how to get it back. But also you don't have to worry about installing packages. They're already, if you defined your container with the right image, they're already, all of the relevant incompatible software packages are already pre-installed, which is also very useful. So in this case, we're just kind of like running defining here, and then essentially this line right here essentially just loads lazily and creates an object that refers and points to the data as if it was locally. This is essentially one of the main the first things that we do in OceanSpy, is read the data, and the only thing you have to do is just define what type of data, which is very, very simple. And essentially what you get here is just an object, we call it the OceanSpy object or ocean dataset object, which contains a lot of attributes. For example, it has the dataset, which is very useful. Again, at this first step, it hasn't got rid of the complex topology. It just created the object, which is the easiest thing to do. But what's also important is that it also creates a couple of other objects. For example, the grid. Anybody who's familiarized with XGCM, even if you're only working locally within one phase that already has the right orientation that you're interested, you still need to define a couple of things so that you're able to just make a plot of surface vorticity or something. In this case, OceanSpy, just by loading the dataset, it already creates the grid object within XGCM. And anybody, again, familiar with this dataset, is that you need to define phase connections to be able to create this grid object, where it already has it right here. It already does it for you. It already is contained in, actually, you can extract those phase connections. Like I said, in this example, we have about a couple of variables, potential temperature, salinity, SSH, the sonal velocity, and sonal and meridional UV velocities. We have more variables that are not publicly available yet, but this is essentially what this is enough for do a tutorial, and then some interesting plots. But this is essentially all of the data set that we have here. So we have the grid, center and corner points, some grid metrics, the coordinate dimensions. We have about, I think it's about 10 days worth of data set for all of these variables, and it already is about 84 terabytes, which is huge. Again, and you're just referring and pointing to the data as if it was local to your computer, which is great. And then I think this is a step that is actually very important in OceanSpy, how to get rid of this complex topology. Well, the best way to do it is just the easiest and best way to do it right now, as it is within OceanSpy, is to define a subdomain within the whole data set, bounded by longitude and latitude, depth and time, and as well specify which variables you're interested in this in looking into within this subdomain. When you do that, there's a couple of parameters here. There's some of them are fixed. For example, this transformation parameter, you want to center at the Atlantic just because of the range of latitudes and longitudes that I defined. It's going to be around the Atlantic, North Atlantic. And the type of transformation, this is the only type of transformation that we have right now, even though some other more interesting looking ones are possible. This is essentially what it is. And you just run a line essentially that it's to say that just as a cutout. And essentially what it's going to do is going to have something that looks like this on the right, top right, a cutout subdomain, figure out essentially which faces survive the cutout that within the domain that you're interested, transform that if they need to be transformed, that is to say that rotate them, flip the velocity vectors or something like that, and it figures out all that for you. It only needs to be done once. It's all lazily so that it doesn't trigger the calculation. That's also very useful because it is able to manipulate all the big data set quite rapidly. And again, because this is within SciServer, then this cutout just feels the data as if it was local to the code. And actually I timed how long it takes here to do the cutout, and it took about 1 minute and 40 seconds, which is great. In a minute, you already have a subdomain that you're just only interested. You don't need to download the data into your cluster, into your institution. It already is there, the code local to your data. And then within 1 minute, you already have a cutout that doesn't have complex topology and the right variables, grid objects, and no longer face connections is needed, and you're ready to go. So for example, here we're just gonna make a plot of sea surface temperature. Look at that, this is great. That's a really beautiful photograph, Iceland. So the subpolar front, which is on top of the Greenland and Scotland ridge, which is really beautiful. And I think it's the surface, so it's essentially 0.5 meters below the surface. And just a single snapshot, just making this plot took about 4 seconds. Again, it's a lot of data. I think I plotted all of them, or maybe every 2 points, so you can have even better resolution. But for this, the more resolution sometimes in this plots, it just essentially means it takes longer, because when you plot, actually you trigger the calculation. So in this case, just plotting actually triggered a couple of calculations just to make this plot. Again, because phase is no longer a dimension, there's no complex topology, and you already, when you create the cutout, it already recreates the grid object, and it's really easy and very straightforward to interpolate within your data, get gradients. And in this case, for example, you can, this line computes the curl of the velocity field. Again, because there's no need to interpolate across faces, it's really straightforward. And here's a plot of the same domain, and took about 7.5 seconds. Again, you had to, when you plot, actually triggers the calculation. So that's why, because you actually have to compute gradients, that's why plotting sea surface, the relative vorticity of the surface, takes a longer time than just plotting temperature variable. Let's do something a little bit more interesting. Let's do sections, vertical sections within our domain of interest. In this case, I'm just picking 2 of them, one along the Greenland Scotland ridge. So you see right here what that path of that vertical, the red one, is going to be, and one across the Greenland Scotland ridge, particularly following a glacier path that was reported in the literature across the Iceland Faroe Ridge. So let's just start first by calculating. So it's, again, a lot of these functions are already written into OceanSpy, so it's really easy to just to calculate, compute, and then plot these vertical sections. The only thing you need to do essentially is just supply the survey points, essentially latitude and longitude, and the variable and depth range, and just a single snapshot. You can actually have more longer time range, and that's it. Also, of course, in the variable list, which velocity, which variables you want them to be included within this vertical section. So this cell right here is just you can modify it. It's available for you to modify. You can play with it and see actually some other range of some other different paths. I think this is kind of relevant for our group right here. And it takes about close to 2 minutes because there's a lot of interpolation that needs to happen. You need to pre-process the data. Again, most of it is lazily done, but some of these things actually are kind of computed as they're done, especially some of them. I'm not going to go into detail, a lot of them. So this is the one that's, I think this is the one that is along survey. And then this is the one that is across the data set. And again, it's a time range, single snapshot, about approximately the same depth. And then you provide the range of latitudes and longitudes as just kind of like a line path. And then, yeah, if you're interested more on this function, you can go to the website for OceanSpy, which I'm just going to open right here. And I'm going to leave it right here. So we have a documentation here where you can actually look through and maybe potentially other tutorial notebooks and stuff, but you can actually go into detail into what does survey functions do. There's other ones, mooring functions. It's a very interesting functionality of OceanSpy. Again, this one was faster because this is the one across the ridge. So less data, particularly to interpolate, so it's actually easier. So now let's look at it. Just to compare, we started with a huge domain, the whole globe essentially, just 10 days, but still a lot, high resolution data. So it was about close to 45 terabytes. And then we created from it, just extracted just a very little subdomain of it. Some interpolation was needed, but our mooring, essentially our sections, numerical sections, are just very little memory compared to that. And now let's make them a plot. Again, this is the plot that I showed before. The red is the one along the Greenland-Scotland Ridge, and the white one is across the Iceland-Faroe Ridge. And then here you go. To plot them, there's another, OceanSpy has a couple of plotting functionalities related to the functions that are written already there. So in this case, you just call the function, and then you can define a couple of parameters that you're interested in. It uses a lot of matplotlib, but also uses a lot of X-arrays. So this is kind of consistent with X-array, the plotting of X-array. And then with that, this is it. This is a vertical section that we've made along the Greenland-Scotland Ridge that you're seeing temperature, potential temperature, and a couple of contours for potential density. And you see like really cold water coming from the Arctic flowing south. And then this is Iceland over here, Faroe Islands over here, close to the right. And then you see overflow water. You see the polar front here over on top of the Iceland-Faroe Ridge, and then Faroe-Chandler Channel. And then this is salinity, I think. Yes, salinity, the same plot, but now salinity. So you see really fresh water flowing south, warm, and then saline water flowing north. You see some overflow water also, not as fresh, flowing south, and these gaps along the Greenland-Scotland Ridge. And then now you see a section across the Iceland-Faroe Ridge. This is potential density. This is the Iceland-Faroe Ridge, beautiful plot. And then one of the things I think that it's really useful, OceanSpy, is to compare against observations, because a lot of the way it calculates moorings and survey sections is actually mimicking what you would do in a boat. Not entirely exactly what you would do with the glider data, but this is one of the reasons, one of the objectives of OceanSpy is to kind of like help people who do a lot of observations and want to compare against simulations. You sometimes want to not only compare against the same time range, but also just applying the same interpolating or smoothing factors as your observations with data, so that it's more relevant, the comparison. So this is not the same time. This is 2013, a section by Nick Beard, but it's just like looks really nice, the comparison. And I use the color maps to kind of mimic what he did in his paper, which is great. It looks great. And towards the end of the data set, I just want to say that there's a couple of good practices when using this kind of software packages is to create checkpoints. I kind of have commented here, but I mean, you can uncomment them. And so because you're transforming data, I'm not sure, I think in this case, you transform just a little bit, maybe not because it ran really fast, the notebook, but when in the case you transform data across multiple phases, there's a lot of operations being lazily done. You probably want to create a local copy so that store them in your Scratch directory, and then maybe so that you don't have to transform every time that you access the notebook. And then this is just a demonstration of how the whole data set can be transformed lazily, the whole data set. And so it's, again, in a minute, you just transform the whole data set without any cutouts, all time and depth and spatial to recreate. So with that, you would be able to create this plot over here. I think that's it for me. I encourage you to play with these notebooks. There's a couple of things that I could say, but I think we'll leave that for a later tutorial video when we have more data. This is just 10 days, so it's not much, but we'll have more to play with around. Thank you very much, and I hope this was helpful. And if not, you can reach out to anybody in our group. Yeah.